Hi, everyone. Thanks for tuning in to today's webinar. Today, we will be talking about recurrent neural networks. So my name is Chloe, and I am a data scientist here at the LKS-CHART Center for Healthcare Analytics Research and Training, also known as CHART. So this webinar will be focusing on the basics of recurrent neural networks, and we will be going over some applications. The goal of this webinar is to give you a high-level overview of recurrent neural networks. And this webinar does not assume any prior knowledge of machine learning or of deep learning. So let's start with an outline of the webinar. So the webinar will be split into two parts. So first, we will be looking at the basics behind recurrent neural networks, which I will refer to as RNNs from now on. We will talk a bit about neural networks before jumping right into RNNs. I'm hoping that after this part, you'll understand the intuition behind RNNs. And next, we'll be looking at applications of RNNs. So for each application, we'll be looking at two examples, a more general example, and then an example that is more related to the clinical domain. So we'll be looking at translation. And the first example will involve translation from one language to another. And then we'll see how we could potentially use translation to help us with medical coding. And next, we'll be looking at outcome prediction. So we'll first look at outcome prediction in the context of sentiment analysis. And then we will look at it in the context of predicting clinical outcomes in the hospital. So let's get started. And dive right into the basics of RNNs. So RNNs are a class of neural networks in which connections form a directed graph along a sequence. So essentially what RNNs do is they use their internal state to process a sequence of inputs. So in this animation here, the internal state is shown with the circle here in blue. And what's important here is that the RNN allows us to process a sequence of inputs. So RNNs are used in various tasks. They are used for machine translation. So that is translating text from one language to another. They are also used for handwriting recognition. So that is, they'll take as input a handwritten document and then interpret it to a text output. RNNs are also used for grammar learning. So this involves learning a grammar from a set of observations. RNNs can be used for text-to-speech applications. So in this case, the goal is to synthesize natural-sounding speech from text input. RNNs can be used for speech recognition. So this is the opposite of text-to-speech. And in this case, we are going from spoken language to text. And RNNs can also be used for prediction. So that is predicting an outcome based on a sequence of inputs. So before we proceed any further, let's take a step back and look at a single neuron. So a neuron is a unit that receives inputs and computes an output. So as you notice in the animation here, each of the inputs of the neuron has an associated weight to it. So the inputs are here. As you can see in the animation, there are 3 inputs. So what the neuron then does is it applies a function on the weighted sum of the inputs. So here, it'll sum and it'll apply a function right here. So what we can do is we can then combine and assemble multiple neurons together. So the output of a neuron can then become the input of another neuron. And these neurons can then be organized into layers as shown in the animation here. So as you can see, there are multiple neurons here, and the output of one neuron then becomes the input of another neuron. And through machine learning algorithms, we want to learn the parameters of our models. So this is what forms a neural network. Now, RNNs, as I've mentioned before, process a sequence of inputs. And they do so by using their hidden state to remember the past. So in this diagram here, the hidden state is represented with the green rectangle labeled as A over here. So when it comes to RNNs, the output is dependent on the computation of the previous time step. So RNNs will read in a sequence one element at a time. And if you notice in the diagram here, there are two arrows that are actually pointing to our green rectangle, two arrows pointing to our hidden state. So there's an arrow from the input to the hidden state, and there's also from the hidden state, there's also an arrow pointing from the hidden state back to itself. So let's unroll the RNN and look at it a bit closer. So our input is a sequence that is denoted by the blue circles. So you have x0, which is the first element of the sequence, x1, which is the next element, x2, and so on here. So let's focus on what's happening right over here at element x1. So as you can see, the input to the hidden state is x1, but then also the hidden state from the previous time step. So here you have the hidden state from x0, which becomes the input to the hidden state at x1. So essentially at each time step, what you're doing is you're reading the element that's at that current time step. So here you're taking it as input x1, and you're also taking as input the context from before. So let's look at this more concretely with an example. So here we're looking at part of speech tagging. So what part of speech tagging consists of is assigning part of speech tags to each word. So part of speech tags are, for example, nouns, verbs, determiners, adjectives, and so on. So the word dog is a noun and the word ate is a verb. So part of speech tagging is useful, for example, if you're building a text-to-speech application, just because words will have different pronunciation if they're a verb or a noun, for example. And that's why knowing the part of speech tag will be super helpful. So remember, an RNN reads in a sequence of inputs. So here, the RNN will read in the word and the context from the previous word to make a prediction. So you can imagine that context is important, especially in part of speech tagging, because the tag of one word has influence on the tag of the next word. So if you know that the previous word was tagged as a determiner, then you can imagine that the current word will most likely be tagged as a noun or an adjective as opposed to a verb. All right, so let's look at applications of RNNs. So the first application we will look at is translation. So in translation, what we are doing is we are going from one language to another. Or rather, we are going from one sequence of words into another sequence of words. When it comes to translation, we actually use two RNNs. So the first RNN is known as the encoder RNN. And what it does is it takes as input text from one language. So it reads in text from the source language, one word at a time, and each time it reads in a word, it updates its hidden state. So the final hidden state of the encoder then becomes the hidden state of the decoder RNN, which is the second RNN that is used in translation. So the decoder RNN then needs to start decoding that hidden state. And what the decoder RNN will do is that it will output text from a different language. And it does so by generating words. So notice in the decoder that there are arrows pointing from the output words into the hidden state at the next time step. So the output word of the decoder then becomes the input at a next time step. And what this tells us is that the words you say depend on the previous word you had just said. So this is how we are able to go from a sentence in one language into a sentence to a different language. So we just looked at translation from one language to another, but we can also think of translation in terms of medical coding. So medical coding is essentially the transformation of healthcare diagnosis and procedures into universal medical alphanumerical codes. So for example, the International Classification of Diseases codes, which is commonly referred to as the ICD codes. So medical coding is important, for example, when it comes to billing or hospital administration and for public health reasons. So in medical coding, what we'll do is we'll take input from a medical text, for example, a death certificate, and we'll output a sequence of ICD codes. So here, instead of translating from, say, a French sentence to an English sentence, what we can do is we can translate from text from a death certificate into a sequence of ICD codes. And we do this using the same architecture that we use to translate from a French to an English sentence or from an English to a French sentence. So now let's look at outcome prediction. So in this example here, we are looking at movie reviews. So the recurrent neural network is taking as input a movie review, and it's reading in that review one character at a time. And what it's doing is that it's predicting the sentiment of that movie review, so whether it's positive or negative. And in the animation here, you'll see that it'll predict the words will be green for a positive sentiment and red for a more negative sentiment. And you'll notice that the polarity, so whether the review is positive or negative, changes as the RNN sees more of the text. So the review starts out as positive in the beginning, and then as the RNN sees more of the text, it switches to negative towards the second half of the review. So we can look at outcome prediction in more of a clinical context. So the next example I'll show you is one that we're actually working on here at CHART. So in this project, we are essentially building an early warning system for the general internal medicine ward. And we're taking as input lab tests, vitals, clinical orders, medications, admission notes, nursing notes. So all things that are stored in the hospital system. And what we want to do is we want to predict whether or not a patient will transfer to the intensive care unit, also known as ICU, or whether that patient will die. So more concretely, our goal is to assist physicians in the general internal medicine ward in identifying patients that are at high risk. And here we're looking more specifically at patients that are at risk of being transferred to the ICU or of dying. And we want to be able to identify these patients 12 to 24 hours in advance. And we do so using routinely collected hospital data. So this data consists of lab results, vitals, clinical order sets, admission notes, and nursing notes. So this is all data that is available in the hospital system. So from all of this data, we create a timeline of events. So we start at time t equals 0 all the way till t equals n, so the end of the visit. And at each time step, so at every hour, we record the lab tests, the vitals, the orders, and so on. And we record these at every hour. So now what the recurrent neural network will do is it will read each of these columns one time step at a time. So we'll take all of the values that we have for time t equals 0, then all the values that we have for time t equals 1, and so on. And that's how we'll be able to process all of this data and essentially make a prediction. So one thing I want to mention is that keeping track of context is a good thing, but after a while, some past events just aren't as important. So for example, knowing what happened at the very beginning of the visit might not be relevant. It might just lead to confusion. So what we do is we use a very specific kind of recurrent neural network called a gated recurrent unit, also known as a GRU. So the GRU is a type of RNN which also has a reset gate right here and an update gate. And what these do is they decide which information should be passed to the output. So basically, the GRU can remember information from a long time ago, or you can simply choose to reset that information. So in this webinar, we went over the basics of recurrent neural networks as well as examples of applications. So we looked at the intuition behind RNNs, and then we looked at two very specific applications. We looked at translation, so translating from one language to another, and also translation in the context of medical coding. And next, we looked at outcome prediction. So in our first example, we looked at predicting movie reviews while taking as input one character at a time. And then we also looked at outcome prediction more in the medical context. So predicting ICU transfer or death from a timeline of medical events. So the main takeaways of this webinar are the following. So recurrent neural networks, they process a sequence of inputs, and they do so using their hidden state to remember the past. And also recurrent neural networks have multiple applications in the clinical domain. So we only saw 2 applications today, but there are many more applications that make use of recurrent neural networks. So this concludes the webinar for today. Thank you for your time. And if you have any questions, feel free to tweet us questions or to email us at the following contact information below. Thank you.